Hey, what's up? Uh, so over the past day, I've been working on this project where I was inspired to create a spinning cube using ASCII art. Like obviously, there was that one very famous donut that was spinning. I didn't want to make any deobfuscated C code or anything like that, but I did want to test my waters with the C programming language to see if I could make something similar. And yeah, so um, I also I'm primarily using the Linux, like specifically WSL. So as you can see, this is kind of what the output looks like. For some reason, it's a lot faster in Linux. I honestly don't know why, but yeah. So talk about how I did this. So you can see the main function is pretty simple. Um, just has a while loop and it will always render. I did initially have a sleep, but I am getting rid of it. And I'm being fine. And I had this rotation time, which I incremented. And you'll later see that this is applied within a cosine, um, or a sinusoidal, like a sine as well. And yeah, so this kind of just keeps track of something that's moving, which is the rotation, specifically the angle in degrees. I every time this runs, it'll increase the degree of the rotation by 0.01. Yeah, okay, so let's talk about what's in this render loop. So every iteration, it'll run this render once. Um, but yeah, I guess I can look at a thing in the code. You can see like standard stuff, uh, um, some include statements, some uh, definitions of some methods. Okay, so the main thing, or I guess the original thing, is this model chords. The model chords and the triangle chords emulates what a .obj file represents. If you ever get a .obj file, there's going to be some vertices, and then there's also going to be some triangles that represents the faces. So you can kind of see there's 12 faces, and each one of these are triangles. You can also have quadrilaterals in OBJs, I'm pretty sure, but that's a little bit complicated, and I'm not. I'm like, first of all, I'm just having a cube, and second of all, like, um, yeah, like that's kind of out of the scope of what I've dealt with. So in this case, 157 is saying the first index, the fifth index, which is 0, 1, 2, 3, 4, 5, then the seventh index, which is this one, um, all makes one triangle. And an important thing to note is when you're looking, uh, let me just quickly like draw this with white pad, or sorry, whiteboard. Um, like we can have a 3D plane that looks like something like this. X-axis, Y-axis, and Z-axis. And then let's say I create this triangle, or sorry, square. Um, and the square is a little bit weird because the middle is 0, 0, technically. So it definitely doesn't look like the most accurate. Um, and yeah, if we look at the first coordinate, -1, -1, -1. Oh, also, by the way, it's a 3D plane. However, there's going to be four coordinates. The fourth coordinate is going to be the homogeneous coordinate. Basically, just initialize that to 1. In OBJs, there's also going to be the normal vectors for each. Is it for the vertices? Yeah, it is for the vertices. For each vertice, there will also be a normal vector, which represents kind of like these types of arrows that are going to be perpendicular. So I guess like technically there's up to like 3 possibilities what the vector could look like. Um, and that's important for whenever we're doing shading and lighting. However, we're not doing anything that complicated. We're not even running this on the GPU. This is a very simple program that everything's ran on the CPU. But yeah, if you set it to like what I was going with that is that the normal coordinates would set the homogeneous coordinate to a 0. That's to ensure that if any translations happen, we'll talk about that when we get to the 2x2 matrices, um, specifically the transformation matrices that we'll be applying. Um, we don't want any translations to occur on the z-axis. However, for position vectors, which these are, we do want them to change. Okay, anyways, so we have the list of vectors, and you can imagine like facing into these coordinates from outside of the box, if that makes sense. So what do I mean by that? I mean, like we're looking at the cube, but we're looking at the cube from outside the cube. And the important thing that I was trying to get to is the order of these have to be counterclockwise from the perspective of outside the cube. So if we look at the front, uh, I mapped all these chords before, but it's kind of annoying. But let's say this is 1. Let's say this is 5. Let's say this is 7. That might not be accurate, but for like, time's sake, and it's just kind of like tedious to kind of just map each output of the chord. But yeah, something to do with this. This could be a triangle, and then 1, 7, 3 could also be a triangle. And as you can see, looking from outside the square, this is counterclockwise. And that's going to be important for when we do area of the triangles. Same thing. It'll be assigned area, but we haven't gone to there. But yeah, so the main thing is these are the list of vertices in total for the entire cube. The order doesn't matter at all. It can be whatever order you want. However, for these, the order within each face does matter. However, the order between the faces don't matter. And yeah, since they're triangles, there's going to be 3 vertices. And then we can also have some transformation matrices. So the way that these coordinates works is we have the x coordinate, the y coordinate, the z coordinate, and then we're going to have the homogeneous coordinate, which we'll just set to 1. And like I guess that is kind of confusing why you wouldn't just have like a 3x1 vector. However, the main reason why is just to make the transformation matrix a lot easier to create. So you can imagine the identity matrix looks something like like this. So whenever this is multiplied with this, you would end up getting the same thing. So hold on. Closer. So yeah, so when this would just be that, would be the same thing. These are all zeros. One's on the diagonal though. So that's the identity matrix. You can scale it with having a specific value here. So specifically, the way that you can imagine this is you're having like a specific coordinate or a specific vector which represents the it represents where we can have our base vectors for the axes. So if the x, y, and z is originally like this, but we want to make it something like like let's say we want to have something like this. And we can make the axes look anything that we want. So, and then we could say that this is x, this is y, and this is z. And let's say y is going to be what is this? Let's just say this is 1 1. So y is going to be 1 1 0, and then just and then 0 for the homogeneous. And then x will be, let's say, 1 -1 0, and then 0. And z will be, let's just say, like -1 0, and then we can still say 1. So if we wanted to draw the object, so let's say it's a cube, we can imagine drawing the object with this axis instead. So this would kind of be, this would be a scaled, it would be scaled a little bit bigger with a rotation as well. And the rotation isn't perfect, so it would be kind of deformed in some type of way that not really easy to think of. And then a way that we could combine these vectors together is just like, if we want to transform it to look like this like deformed mess, we just combine these vectors into one. So x look like that, y could look like this, and then z could look like this. And then we could just have the base values for the homogeneous case. So whenever this vector gets multiplied by that vector, we would have like x would now be this, y would, sorry, I said that wrong. You could imagine, yeah, so I mean you can apply your normal matrix multiplication, but you can imagine the object being scaled like you are putting new axes on the cube itself. And yeah, so in the case that we have, you can see that we're basically having the same identity matrix, but we're scaling the x, y, and z. And oh, by the way, oh, and there's also one here. Ooh, rosy, nothing. Yeah, and also there's a one over here. So I guess like in this case the homogeneous was just the same value, but any values here you can imagine just shift the entire thing along. So if this was like a 3, it would shift it in the x-axis by 3. So it would be here. It would be the same thing, just shifted by 3. If this was like 4, it would shift everything up by 4. And that's really the benefit of having a 4x4 matrix and a 4x4 vector instead of a 3x3. And yeah, so these are just scaling down. Gotta stop cozy. Um, So these are just scaling down all of the axes by a factor of a half. Like you can imagine if we didn't scale one of them by a half, it would kind of be elongated in that specific axis while the others were the same. So that this would be in accordance to the z just being 0, 0, 0. Yeah, and then this scales it everything up forward by the z-axis by 1. So that's like the first transformation, and then this is the second transformation. Um and yeah. Trying to think if that, yeah. It might not be exactly that, because usually you'd want to do matrix multiplications, but like you would want to have one matrix multiplication where it's a scaling factor and then multiply it by the translation. So like, what do I mean by that? Like it's better, instead of to do it like this all in one, to have it as 0.5 0 0 0 0 0.5 0 0 0 0 0.5 0 0 0 0 0 0 0 0. So this scales everything by like, and then take this, and then now we can just do a transformation or translation matrix specifically. And then you can calculate this like just by hand. I'm not gonna do that, but like this is my idea, but I don't know if this is actually the result of that. But I mean it works. But like specifically with the example that I did, I'll kind of like explain this, but I use a Z buffer test, so the Z coordinate actually doesn't matter. So I could technically get rid of that. Anyways, the next matrix I have is this viewport matrix, and I'll explain this once I I have this helper function which can multiply a matrix by a vector. So it takes in the result which you want to where you want to store the result of the um, matrix, and then the result of the matrix multiplication. You take in the matrix that you're multiplying with the vector that you're multiplying with, and remember matrix multiplication rules. 4 by 4. This is a, and then okay, not here specifically. So it's a 4 by 4 times 4 by 1. These two have to be the same, and then the result is a 4 by 1. So it's a vector. And I store it in result. So yeah, and it's just storing it. The presentation. Remember to clear. And then I have this function. I looked this function online. It is able to, you're able to pass in 3 vectors. You're able to find the triangle area. It essentially collapses the z coordinate. So obviously there's no z coordinates that are found in here. So it's not taking like the 3-dimensional area, but instead you're taking kind of the 2-dimensional area. But that's fine for our case because we use a technique called rasterization, which I'll get to when I'm talking about the render function. And yeah, the important thing to note is whenever you input these vertices, you want to make sure that the vertices are made in the counterclockwise order. Otherwise, you'll end up resulting in a negative area. However, we don't have to worry about that since we did that already. Here, whenever we created our .obj file, like we made sure that they were all counterclockwise, so it ended up being bad. So we don't have to worry about that. Okay, so let's talk about the render function and how it specifically renders the cube to the output. I first have this Z buffer. Z buffer, basically, this is what I'm going to be printing the output. So that you can either think of this as the result. The reason why it's called a Z buffer is because, like, I guess, I mean, you could just call it result. This is kind of more of a technical term for, uh, whenever you have to compare different vertices and see which one has the greatest Z or the most negative Z, depending on your use case. So what I mean specifically is like pretend like this is the cube. If I'm looking at this pixel, there's going to be like um two Z's, if that makes sense, 2 pixels. One that's associated with uh this face, and then the other that's associated with the face of the, the square behind it. And you need to only print one, otherwise there could be like random things, and like you obviously can't see through the cube. If you don't print it, then then it's printed by the order of the fragments that you look at, which is obviously like not what we want. So the Z buffer will ensure um, that if it's behind something, we won't be able to print it because we'll store the greatest Z. And since the way that we do our output, the Z is eventually just the thing that we print. This could just be result, honestly. not that useful to call it z buffer. Yeah, this is just setting everything to a -10. It's better to keep it to -1e9 or like negative infinity. I set it to -10 because I was doing some debug. And yeah, okay. So now we're gonna talk about the rotation matrix. Um, or I guess specifically this applies the matrices. So we're on to our first stage of the rendering pipeline. Okay. So initially we have um so we have um our cube. Uh, I wish I could draw a little bit better, but best I could do. And you can imagine this has all of the coordinates. I'm not gonna care specifically about what the coordinates look like, but these are the coordinates that I wrote here. So something like that, -1, -1, -1, 1, like that, 1, dot, 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 all the way around. Um, so these are the model coordinates. You can think of each stage of the pipeline, we want to transform this in some way where eventually we could have a screen that's what is my screen? My screen is 42 by 42. Very specific number. But it can be whatever number you want. And you can imagine like if there's a cube here, this could be any numbers. So let's say like this is like the middle. So like x could be like 21, and then the y could be let's just say 5 or something like that, right? So we're basically transforming uh this until it's what we want, and then we end up with uh, the final finished product. Looks like that. And yeah, so we first um so this is kind of like the loop. We iterate through every single row. We have 12 rows, I'm pretty sure, and the rows, 8 rows, sorry. So we iterate through every single fragment, and we want to then so like the fragments, or sorry, not fragments. We through each of the coordinates. So these are the coordinates. There's 8 rows, and then we transform each one of these vectors. So we're basically passing it into the vector that we kind of talked about earlier. So like we have a transformation matrix. We pass in one vector, then the second vector, then the third vector, and then we're updating that vector. Yeah, and we're gonna have some temporary vectors. We don't want to change the global vectors, otherwise rotations would, and like translations especially, will always propagate through. So like if you transform it by one uh shift the first, then it'll do by 2, then the next, and then 3, and then like scales will keep getting bigger and bigger forever. So you want to have some like temporary like stages. And yeah, so we first start with a model stage, and then we want to do some type of transformations. So in my view, I first do a rotation. Uh, so like it can rotate however it wants. So say it looks like something like that. You can imagine this is just like rotating like that and that a little bit. Um, so like this is what is that? You have to use the right hand rule. It's a little bit annoying. That's a Y rotation. this is an X rotation. Um, and yeah, so that is a rotation, and then also the scaling. This is called the model view matrix. Model view. And then now it's in view coordinates. And so view coordinates is gonna be what we are looking at, like eye space essentially, what the camera is looking at. And after the view coordinates, I then apply like the pixel matrix, which people call the viewport matrix. Is yes, the names are kind of like misleading, kind of like hard to understand. But like the model view matrix is a pretty like common term. This is, you can call this like camera space. And then the viewport matrix is applied, which then puts this puts it into pixel coordinates. And pixel coordinates are what we want to output at the end. So yeah, so two matrices. You can have many different matrices within the model view. So in my case, I have the X rotation matrix, the Y rotation, and then the this is the scaling plus translation. But like I call that one the model view, but they're all part of the model view pipeline. Yeah, and the order does matter. So I do rotations and then the translation. If you do the other way, if you do a translation and then rotations, it would translate. So like, let's say I translated up, then it would translate each of the whole object up. But then when you do the rotation is going to be bounded by the origin. So then you can imagine if you rotate by 90 degrees, um, it's like if you translated it in the way that it ends up going. So like let's say you translate it by the x-axis by 90 degrees. So that means uh from here, or I'll just say 45 degrees. Or okay, I'll look in the 2D space just for it to be a lot clearer. Let's say I rotate it like that way. Then it would look something like this. And then if I do a transformation after, let's say I transform it up, uh, that would transform it like that. So you can see this is the same as if I translated it like that, and then I did a rotation. So like what I mean is if I flip the order, so this is rotation, then translation up. So if I do the translation up, then it'll be this. And then if I do the rotation, wait, hold up. I did my ordering wrong, sorry. We do the translation and then we do the rotation. The way it works is yeah, sorry. It's a little bit unclear. So we have like the list of all the vectors, but if we do the translation first, that means we take the matrices, which is like a big rotation, and then we have like, oh, we have like vector 1, and then that stores to the new vector 1, and then vector 2, that stores into the new vector 2. And then we inspect the output, then it'll look like this, right? Like everything is like rotated. And then if we do a translation up, it does it based off of the origin. So what that means is it looks like this. And if that's what you're looking for, perfect. And if it's not what you're looking for, well, then you need to think about what happens in the inverse case, which you do the translation first. If you do the translation first, it'll go up. Translation first, it'll go up. And then if you do the rotation, then it'll go this way, if that makes sense. Because it does everything by the order. or at least the entire object. It applies whenever it applies a rotation or a translation, it does it by so if you do the rotation first, that's kind of like this case, right? Where you do the rotation first and then a translation. It's a little bit easier to control where the translation should. So I do the rotation, then I do the translation. This just scales it and then translates it forward. Okay. Now let's talk about the rotation. This is kind of like you can use an equation to make it a lot easier, but remember the rotation timer. Uh, this is kind of just like what the transformation matrices look like for rotation. I won't really go into the specific implementation and how this came to be. If you want to look that up, you can get a lot more clarity on it. But yeah, this is able to transform by rotations. And when we apply that, we're basically just having the matrix multiplication 3 times for each fragment. And you can imagine this is happening 8 times. So this can get really slow, especially with a lot of fragments. A lot of times, whenever you're using something like OpenGL or Vulkan, you'll want to create all of these matrix multiplications within the GPU itself. You won't want the CPU to do it. Obviously, in this like naive, very simple approach, it does everything on the CPU. However, doing everything on the GPU, the whole reason why the GPU was made was to be able to run graphics and do matrix multiplication. So the way that it does it is you have to use something called a shader, which basically just means that's being applied on the entire, or that, yeah, that's being uh, applied during the GPU format. And this whole section is called the, or I guess specifically, um, for me, since I'm not applying, yeah, so this whole part, we can call this the fragment shader. Uh, yeah. Usually the pixel coordinate, like the viewport, isn't in the fragment shader. However, for me it is. And I guess like, yeah, now looking at this, this could have been put in the for loop. Let me just change it quick. However, usually in the whenever you run OpenGL, you don't actually want to run the pixel coordinate and the fragment shader, and that's because the fragment shader, you can think of it as we have all these fragments and we're applying these computations based off of them, and yeah, and any transformations is applied during this fragment shader. However, whenever you're dealing with actual shadows and actual shaders, then um, the fragments will create some type of, like, we'll want to store the normal, but then later on there's another shader called the vertex shader. And I feel like vertex shader is not a good name. It should be like a pixel shader or something. And then at the pixel shader, it applies like at literally every single pixel. It applies the lighting to know exactly where everything should be. But yeah, for the fragment shader, and for our simple approach with no lighting and no shadows, this is sufficient. Okay, I have small z, biggest Z for to know eventually with the ASCII ranges. But before we get into that, um, now we have our entire model that's transformed exactly how we want to look. Now we want to actually do the rasterization. The rasterization step, basically, we have like a list of vertices, right? So we have 12, or sorry, we have a list of faces. We have 12 triangles. You can think of it um like we have the triangle chords, and there's 12 triangles in them. Each triangle is a fragment. So yeah, we're going through each fragment and we're rasterizing it. What does that mean? We have let's say we have this screen. We have this random triangle. You can imagine we have a lot of triangles, and each one has an X, has a Y, and has a Z. And to do this rasterization step, we first create a bounding box. And the bounding box is just kind of like, okay, what is the minimum X coordinate, minimum Y, and maximum X, maximum Y. We don't need to deal with the Z since we're kind of like uh squishing the Z in total, but we're the Z buffer test, like this whole thing is in the Z buffer. So at the very end we check. But for now, since we're iterating through each fragment, we don't have to worry about the Z until later. And yeah, so we have 3 vertices, and we have this bounding box now. And now you can imagine, you could just like iterate through each pixel, if that makes sense. So each pixel could be inside the triangle or it could be outside the triangle. And that's basically what I do. So we have uh the triangle bounding box x min, x max, y min, y max, and then we go through each one of the 3 vertices. So remember, like we have 12 fragments, and then we're setting the bounding box to the triangle, or we're looking at the triangle and we're saying, okay, what is the minimum x, minimum y, maximum x, maximum minimum y, and yeah, and then from there, uh, we create a double for loop where we go. This is like, okay, because like technically the bounding box could be out of bounds, and if that's the case, like we want to make sure it's 0, and it could also go out of bounds the other way. However, in my case, that's not an issue, I don't think, but it could be an issue. And yeah, so we iterate through each one of the pixels of the bounding box itself, and then we want to check. We want to check, okay, how do we check if a pixel is within the pixel? And if we do, how do we check where that coordinate is? Like, what is that coordinate? So we're gonna be using a technique that's requires us to find the barycentric coordinate. So what that means is we have like an x, y, and let's say this is A, B, C. Remember, counterclockwise, just easier. And let's say we have a point P. Okay. So we have little a, little b, and little c. And the way that the barycentric coordinate works is like we first calculate each one of these areas. So we can have the total area, which is, remember that we made that function which finds the area of the thing. So we could just say area of like A, B, C. And then we can have little a, which is going to be the percent that this triangle's area is relative to the total area. So it's going to be the area of P, remember counterclockwise, so we need to be a little careful. So PBC divided by total area. B is going to be the area of, what is this? This is PAC divided by total. And since this is a percent, this is going to be 1%, this is going to be the other percent. The other one is going to be the 1 minus the, say, C is equal to B. Yeah, and we're dealing with this entire bounding box. So if we ever do something like this, let's see. Let me just create like a new drawing of this. So let's say this is A, B. So A, B, C. Let's say we have this P here. So same thing. Um so whenever we do this, we can think of like A will have its uh like area here, then B will have its area here. Now C, it's a little bit hard to like wrap your head around, but C will actually have its area here. It'll be the negative area. And this is the power of why we're doing the barycentric coordinate. We're able to check if any of them have a negative value, which means it's a like obviously area is unsigned, but like with the equation that we use, we're getting an unsigned we're getting a signed area, which means if any of them are negative, we can immediately rule out that point. We can remove that point, just not even use it because we know that point's going to be outside the triangle. And yeah, that's basically the thought of it. But also like another important thing is you can think of the barycentric coordinate as how close it is to that vertex. So like why might that be important? Uh, well, we have the x and y coordinate of this P. It's just like x and y of wherever it is in this bounding box, but we don't have the z. So whenever we want to find the z, we can kind of like take this average of a, b, c, but using the a, b, and c. So since it's the percent, we can just do a times the vertex a's z's coordinate plus b times the vertex b's z's coordinate times plus z is the like remember is a percent of how close it is to C times C then the coordinate of Z. This is going to be the Z coordinate of that point P. So this equation is also pretty handy for determining what the Z value is. And okay, uh, and that's essentially what we're doing within that loop. We're iterating through each one of the fragments. Yep. So this just gets the v0 this just puts the pixel coordinate um and then the x. So so we have three vertices within I. So triangle coordinate, remember this represents a fragment. So triangle coordinates has a 12 fragments. So if I is 0, we're looking at this fragment. If I is 1, we're looking at this fragment. And we're saying, okay, of that fragment, we care specifically of the x. So of that fragment, or sorry, we don't care about the x. We care about the first, or the 0th vertex. So this is the 0th vertex, this is the first vertex, and this is the second vertex of that entire fragment. So that's why like when this is 0, this is 0. When this is 1, this is 1, this is 2, this is 2. And then the 0 because it's x, the 1 because it's y. Because this will return the index of the triangle, or sorry, this is the index of the vertex, and pixel coordinates is the list of vertices. Remember models row is 8, there's 8 vertices. So of the 8 vertices, it's caring about like which vertex. And then obviously we did all of the matrix multiplication already. Okay. And then yeah, so this just allows us to call some of the functions later on a little bit easier. We can get the total area in this function. If it's 0, just in case, like I don't want any by zeros, say continue. And then this goes through each value of the bounding box. Then it calculates little a, little b, and then little c with the same implementation that I kind of showed. This honestly isn't required. However, I thought you kind of had to test if the uh if like if big areas is greater than 0, then you want to check if any of them is less than 0. But I'm pretty sure if you're assuming all the coordinates are counterclockwise, I think it would ends up being fine. But yeah, uh, so you can get rid of this. But if they aren't all counterclockwise, I think once you get to here, if you have this approach, I think it ends up being fine. And yeah, this is calculating the current z coordinate. I could have done this a lot better now that I'm thinking this. But we're getting the second index, which represents the z of this is saying vertex 0's z, vertex 1's z, and then vertex 2's z. So exactly how I talked in this. Okay, yeah. And then this is where the z buffer comes in. It's just saying, oh, if the current z is greater than the z buffer. And that's why we should set the z buffer all to negative infinity initially, because if we set it to 0, hey, some of them could be negative, but not it could be like -1. But then it would never replace a 0. So if you set it all to negative infinity, then at this point it ends up being fine. The z buffer and then kj, I iterated through the wrong way, kind of like the unintuitive way, where I iterate through the columns and then by the rows. That's why like some of them are flipped. This one xy, but yeah, over here it's opposite way. So the row and then the column equal to the current, and then this just prints it out. And then yeah, that's basically it. I can kind of show how I print it out. I don't. I kind of just found this online. Something to do with the ANSI like escape characters. I don't really get it, but this just puts your cursor at the top left, which is like home. Where the H is home. Um, you can get rid of this line if you wanted to like spam outputs, but I thought it would look a lot cleaner if it like updated. It kind of looks like an animation, I guess. Yeah, and then we iterate through the entire window Y, window X. Um, and store the current buffer, and then I wanted to have it turn into like the ASCII scale. So I looked up online, someone kind of had a scale of like every single ASCII character. And I just like picked some of the cool ones. So apostrophe, semicolon, plus 0, hashtag, ampersand, at, and then $sign. So as you go to the right, it's kind of getting like darker. I guess like gets lighter. Yeah, it gets lighter as you go towards the right, which is pretty cool. So uh we have all the Z inputs for the entire screen, and now I want to map them to values of this ASCII stream. So there are 8 ASCII outputs. So using this formula, I'm able to divide it into one of the buckets, 0 through 8, or 0 through 7. So the way I do this is you take current Z subtracted with small z. This is kind of like zeroing it out, like zeroing out a scale. Yeah, so if current 0 is the smallest z, and also small z, I calculated, yeah, I just like always calculate it. Like, so it's basically saying for the entire cube, because I initialized it before I started iterating through all of the fragments. For the entire cube, what is the smallest z that was ever found on any of the vertices? And what is the biggest z that's found on any vertices? And then, yeah, so using that, so this is the range. So we're basically saying like, okay, take the beginning value, divide it with the range, and then multiply by 8. Because this is going to get the percent that's within the range, and then we multiply by 8, and then we floor it. So it could only be up to that value. But just in case we have, we're basically saying, oh, if it's greater, just set it that value again. If it's less, so if it's negative, that's fine. I just have that as like the cube is not there, right? So like all these spaces, the cube isn't at that location. So I have just an empty space. And then yeah, I just have all the cases of the stream that I was talking about earlier. And that's about it. And then we just do some basic lines. And yeah, that is um how we can get this output. If I don't scale it, it kind of looks like that. Yeah, and you can compile it to see cube dot c dash o dash lm. And then similar with the Windows version, let's just say gcc dash o cube dash obviously put the file gc cube dot c dash o. Oh, I just named it the same, but it's the Windows version, so called cube.exe. And there we go. So pretty fun project. I just got bored. I don't want to show you guys. So thank you. Have a nice day.